These presentations are really a part of community support. Three of the inland amateur radio organizations are listed there at the bottom and above as well. Mendocino Auxiliary Communication Service, MAX, Mendocino County Amateur Radio Communication Service, McCarks, and Willis Amateur Radio Society. Um, these are just your friends and neighbors and fellow hams, and we want to make the hobby more fun for you. So there we go. Now it's working. Let's talk about where we are in this. We are in week 4, session 4, and I'm about to dig in here to the electrical and RF safety. There's 25 questions in the pool, which makes it a little easier, not as much ground to cover tonight. And 2 questions on the exam. So what are the topics in sub-element G0? Well, they revolve around electrical and RF safety, and there's 2 groups. The first group relates to RF safety principles, rules, guidelines, routine station evaluation. And the second group is station safety, electrical shock, grounding, fusing. The first one's kind of focused on RF exposure, the other part on just general electrical safety. And there will be one question from each of the 2 categories on the exam. You'll find chapter 9 of the ARRL General Class License Manual covers this material pretty thoroughly, actually. So let's do this. Let's start off with a review of the segments that we've covered so far. I've got at least one question from each of the segments that we've done in the previous weeks. So let's pop through these and see if we can refresh your memory. From sub-element 6, which of the following is an advantage of CMOS or CMOS integrated circuits compared to TTL integrated circuits? Low power consumption, higher power handling capability, better suited to RF amplification, better suited to power supply regulation. Well, TTL, that's transistor logic. These are logic circuits. They're not amplifiers. Power handling capability doesn't make any sense. The switch from TTL to CMOS was driven because of the lower power consumption. CMOS devices, although a little bit more sensitive to static, consume very little power in their logic functions. Okay, talked about this one last week, I believe, in modes and emissions from G8. Which of the following narrowband digital modes can receive signals with very low signal to noise ratio? That means it'll work even if you can barely hear the signal. Well, if you remember, that's one of the more popular ones, and that is FT8. That's a frequency shift key mode with 8 tones incorporated. So works with very little signal above the noise. Okay. G3, we talked about that a couple of weeks ago, and that's our RF radio wave propagation. Which frequency will have the least attenuation for long distance skip propagation? Well, we talked about the MUF, the LUF, the critical frequencies. Well, the answer is just below the MUF. When you get just nearly to the highest frequency, the maximum usable frequency, you'll find the least attenuation, and that's what you want for long distance skip propagation. Okay, section 7, which of the following is a characteristic of a switch mode power supply as compared to a linear power supply? Lots of ways to take AC and convert it to DC to run your radios. The old-fashioned way is with the linear power supply, which often have very large and very heavy transformers in them. The switching supplies, or switch mode as they refer to here, they utilize a high frequency operation and allows the use of smaller components. So which switch mode power supply going to be a lot lighter, more compact than the traditional linear or analog power supply? One caveat is they can generate RF noise. So in some circumstances, that is a drawback of a switch mode power supply, but they are lighter, smaller. Oh, this is a safety, or this is a, yeah, one that we talked about last week about from G4, I believe, possible effects of a resonant ground connection. What does that mean? Well, you grounded the equipment in your station, and maybe you didn't make that run as short and direct as you can. And if you've got a longer ground, that ground wire can actually become resonant at some frequency. And as a result of that, it won't be an effective ground, and high RF voltages on the enclosures of the station equipment might be present. So you need to, when you're grounding the equipment in your station, you want those grounds to be short and direct and avoid long ones so they won't become resonant and present higher RF voltages. Okay, what's the approximate length of a half-wave dipole cut to 14.250 megahertz? Well, let's see, 468. I think that's the number, divided by the frequency in megahertz. I just know off the top of my head, that's a 20-meter dipole, and they're really handy. They're only about 33 feet long. So half wave, 468. Okay. Which of the following components should be added to a capacitor to increase the capacitance? Okay. We talked about these components, and you can connect in series and parallel, and different things behave different ways. But you're trying to increase the capacitance, so you can rule out the first two answers right away. You're not going to put an inductor in there in any combination with a capacitor to change the capacitance. Now you will create an LC circuit, which will be resonant at some frequency, but that's not what you're trying to do. So you need to add a capacitor. And if you remember, capacitors, you add them in parallel to increase the capacitance. If you add a capacitor in series with another capacitor, you'll reduce the overall effective capacitance. Why do voltmeters have high input impedance, or why should they? Well, when you're hooking up if you're measuring a voltmeter in a circuit, you want the resistance of that voltmeter to be very high, or the impedance to be very high. So when you connect it to the circuit, you don't load the circuit down. If you remember, when you hook two resistors in parallel, which is basically what you're doing with that meter, you're putting it in parallel with the circuit, you're going to have a lower overall resistance than either of the two resistors alone. So you want high input impedance on a voltmeter to decrease the loading. Okay, that was the review. I hope your heads aren't spinning. Let's get into the safety topics. And just because there's only two related questions on the general class exam, don't underestimate the importance of safety. One of the most important aspects of amateur radio is recognizing the hazards that may be present and following all the appropriate safety rules to mitigate those hazards. There are hazards in this hobby that are potentially lethal. So it's important to know those, to recognize those, and take measures so you're not injured. So let's talk about electrical safety and the human body. And we're going to jump back to some reviews from the technician exam material. It's the electrical current flowing through the human body that does the damage. That electrical current can cause heating of tissue. It also can disrupt electrical functions in cells. And most importantly, it can cause involuntary muscle contractions. And why is that a problem? Because if that current is passing through your chest from one hand through your chest to the other, it can disrupt those involuntary muscle contractions in your heart, possibly causing it to stop. Definitely a potentially legal or lethal hazard. So keep in mind, and this goes back to Ohm's law, higher voltages present a greater risk. The higher the voltage for a given resistance, your body, the greater the current. And if it's the current that does the damage, a higher voltage is going to present a higher risk. Really, as little as 30 volts can be fatal. That doesn't sound like much, and it's not. Again, that would probably be passing through the chest. But the higher voltage is because they present a greater risk. That is a reason that a power supply interlock is used, and that ensures that dangerous voltages are removed when a cabinet is opened. That's right out of the question pool. What does that mean? There are compartments, especially in tube equipment, that may have very high voltages present. And you generally design it so when you open the case, there's a switch that will disconnect that high voltage. So when you go in there to work on it, you're not going to be at risk of contacting that. So power supply interlock ensures dangerous voltages are removed when the cabinet's opened. That's the answer to the question. So let's talk about electrical safety. We talked about the human body. Let's talk about electrical safety. The station electrical safety is covered by the National Electrical Code, or the NEC. So aspects of the electrical safety in your station are going to be part of the NEC. One of the things that the NEC specifies, oh, well, we'll get to that, is wire gauge. And there's a couple questions on that, but let's talk about wire gauges. You'll see the AWG, the American wire gauge, with the numbers. So AWG 10, AWG 12. The higher the number, the smaller diameter the wire is. Okay, so number 22 wire is much smaller than number 8. Okay, and why is that important? Well, the higher AWG, the higher gauge wire, the smaller diameter wire, has lower current carrying capacity. And that's where the two questions come in. One of the questions is the NEC specifies AWG number 14 wire is appropriate for up to 15 amperes. So 14, 15, look for those two together, and there's your answer for that question. The sister question is that minimum AWG number 12 wire is used for safely wiring a 20 ampere circuit breaker. Notice a number 12 wire, it's a lower number, but it's a bigger diameter, and it can be used safely up to a 20 amp circuit. Okay, so let's talk about equipment protection, AC equipment protection. From the tech test, there's a discussion, there's a question that says that if you build your own AC powered equipment, you'll want to install a fuse or circuit breaker in the hot conductor only. So there's 3 wires on your 110 volt AC. You've got a hot, a neutral, and a ground. The hot's usually black. The hot is black insulation. The white is the neutral, and the green is the ground. But you'll install a fuse or circuit breaker only in the hot conductor. The technician question, or I'm sorry, the general question brings up the concept of a 4 conductor 240 volt AC circuit. So there's 3 conductors in a 110 volt circuit. There's 4 in a 220 volt AC circuit. So in these circuits, there are 2 hot conductors, 1 neutral and 1 ground. So you would fuse or put a circuit breaker in those 2 hot conductors only. Yep, fuse the hot wires only. Okay, another protective device is a ground fault circuit interrupter, GFCI. And you probably have those all over your house. You should. What they do is they're looking for current that's flowing from the hot wires to the neutral wires, and they shouldn't be. There should be no current there. And if that's detected, that current flowing from hot to neutral will cause the GFCI to disconnect the AC. So that current flowing from hot to neutral will trip the GFI and disconnect the AC, and then you'll have to go push the little button on it to reset it. There are two health-related questions in the question pool, and we'll just cover those kind of on their own. The first question I asked about the dangers from lead tin solder. For years and years and years and years, that's been the standard alloy for solder, 60/40 or various combinations. But it contains lead, and that lead can contaminate food if hands are not washed carefully. Again, the italicized text relates to wording in the question pool. So the danger from lead tin solder is that lead can contaminate food if hands are not washed carefully. So if you've been soldering and you go to crack open a beer or have some chips, make sure you wash your hands very carefully to remove that lead. There's another solution. Use lead-free solder. These are becoming widely available. Melt point tends to be a little bit higher, but you eliminate that lead risk from the solder in your shack. The other question revolves around emergency generator installations. If you're going to set up an emergency generator to power your station or your home or whatever in the event of an outage, the generator should be operated in a well-ventilated area. That's the question and the answer from the pool. Pretty much common sense. Unfortunately, a lot of people are unaware of the risks and the carbon monoxide that can be generated or emitted from a generator, and it can kill you. So again, another potentially lethal thing, and that would be operating a generator in an area that's not well ventilated or ventilates into your home or shack. Another thing I recommend, it's not in it's kind of in the question, it's kind of not, it's there as wrong answers. For my personal generator at home, you'll find the instructions along with operating in a well ventilated area will say that the generator should be tied to a ground rod. There's a ground connector on every generator I've seen. Keep the fuel some distance away. You don't need a can of fuel by a hot generator. And by all means, have a fire extinguisher handy. I store my fuel on the other side of the house. I have a fire extinguisher about 5-10 feet away from the generator. But the question in the pool, emergency generator installation should be operated in a well-ventilated area. Okay, let's move on to the big bang, lightning protection. And again, this is kind of a rehash of some of the stuff in the technician exam, but towers and antennas in ham radio are a natural target for lightning strikes. And those can, there's serious risk of personal and property damage, severe injury. Lots of ways to mitigate that. But the one that the test refers to, one of them is that coaxial lightning arresters, which protect the equipment and look something like this. Actually, if you could see it, you could see it says right here, coaxial lightning surge protector. You'll notice there's a big ground lug on it and places for the coax to hook up. But they protect equipment, and where should they be located is one of the questions, and they should be located where feed lines enter the building. So this would be outside your shack, where the coax or feed lines enter the building. And those should be attached to the station's lightning ground system. That ground lug that I showed you here at the bottom should have a heavy gauge wire that's attached to the station's lightning ground system. And that lightning ground system should be as close as possible to the station equipment. So those are the concepts you'll see in the exam regarding lightning arresters. The other question relates to the lightning protection ground rod. So those should be as close as possible to the station equipment, but they should also be bonded or attached electrically to all other grounds. So that is the answer to the question. The lightning protection ground rod should be bonded to all other grounds. Okay, let's talk tower safety. Um, and amateur antennas and towers bring another set of risks. Many hams utilize towers to improve the location and performance of their antenna system, and towers come with some serious risk. The tower climber um, is exposed to significant risk. You're maybe 50 feet, 100 feet, 200 feet, depending on the tower. Most hams are probably 100 feet or less, but um, so if you're working on that tower, you're exposed to a significant risk. Of course, you tend to think of fall as the serious risk, and it is. Anytime you're climbing a tower, you should be wearing a safety harness, and it's the responsibility of that climber to confirm that the safety harness is rated for the weight of the climber and within its allowable service life. These harnesses do come in different sizes. They're often a mix of leather fabric and nylon strap, which means they will wear out. So they do have a allowable service life that you should not um, exceed. So tower climbers should confirm that the safety harness is rated for his weight or her weight and within the allowable service life of the harness. That will also have a fall arrest lanyard on it. What you don't want to do is tie a harness off to a solid rope, because if you fall, by the time you've started accelerating and you get to the end of that rope, there's going to be such a shock that alone could be fatal. So the fall arrest lanyards um, have a stitching in them. So when there is a fall, that stitching slowly lets go and slows the deceleration. Anyhow, um, other question in the pool about climber safety is if the tower supports electrically powered devices, the power supply to those devices should be locked out and tagged. That's the answer to the question. Any of you, like me, who've worked in an industrial environment, you might be familiar with the term LOTO, lotto, lockout, tagout. That's what you do to make sure that equipment is not energized when you do not expect it to. And in this case, oops, let's see. Um, what that would mean is that you would switch off the circuit breaker and put a lock on it, or some other way of preventing that circuit breaker uh, from being returned to the energized position. That's what the lockout would be. Okay, you saw the preview. Let's get on with a few review questions. So, which of the following is covered by the National Electrical Code, NEC? Well, it's not the RF exposure limits of the human body. It's not bandwidth or modulation. All three of those kind of sound like FCC territory to me. Um, NEC relates to electrical safety of the station. I think we just talked about this. What should be done before climbing a tower that supports electrically powered devices? Notify the electric company? Nah, unground the no. Make sure all circuits that supply power to the tower are locked out and tagged. Okay, so if there's electrically powered devices on the tower, make sure the power is shut off, locked out, and tagged. Okay, so this is something that comes out of the NEC. What size of fuse or circuit breaker would be appropriate to use with a circuit that uses AGW number 12 or number 14 wiring? Okay, so it's a higher number, which means it's smaller wire, so it's going to be a lower current, and actually it is the lowest current in the list, 15 amps. And again, my hint for this, 14, 15. If you see number 14, the answer is going to be 15 amps. Which of the following is a danger from lead tin solder? Well, RF has nothing to do with it. Tin is stable, it doesn't cold flow. No, it's the fact that lead from that solder can get on your hands and can contaminate food if the hands are not washed carefully after handling the solder. Yep, that's true. Keep that in mind, but if you can, use lead-free solder. Oh, where should you locate those lightning arresters? Where should they be located? Well, those go in feed lines. So that only one answer with feed line in it, and that's where the feed lines enter the building. You want to have them outside the building, and of course they're going to be attached. The ground lugs on those will be attached to the station lightning ground system. Okay, into the second section for G0, and that is RF exposure safety. This section was added to the question pool around 1997 to make amateurs more aware of the potential danger to themselves and others from RF energy radiated from their antennas. And it was established to help not just hams and their families, but their neighbors as well. A recap from the tech book, a tech exam. Radio frequency energy is non-ionizing radiation. It's not like radioactive material where it can ionize the DNA in your cells. It's non-ionizing, so there's a little less of a risk associated with it. But one way that RF energy affects the human body is that it heats body tissue. And notice the italics. So this is right out of the question pool. And if you remember, this was discussed in a couple sections, and it might come up again. Touching an antenna while the transmitter is on can cause an RF burn. So clearly, RF energy can heat body tissues enough to cause an RF burn. Okay, so let's talk about the guidelines. It's not the NEC, it's the FCC that has established these guidelines. These guidelines are not limited to amateur radio stations, and these apply to all stations with time average transmission greater than 1 milliwatt. That's not a lot of power output. You may ask, what's a time average transmission? Again, from the question pool. Time averaging is the total RF exposure averaged over a specified or certain time period. I think the question says averaged over a certain time period. So that's what time averaged transmission is. So again, all stations, not just ham stations, and a very low threshold for time average transmission. So amateur operators must take steps to ensure compliance, okay? And the step that is required is to perform a routine RF exposure evaluation. Okay, that's from the question, what steps must be taken? Well, you have to perform a routine RF exposure evaluation and prevent access to any identified high exposure areas. Both of those are part of the answer to the same question. So take steps to ensure compliance by performing a routine RF exposure evaluation and preventing access to any identified high exposure areas. So let's talk about the exposure guidelines. So what are ways to determine that a station complies with those RF exposure evaluations? How will you do that routine evaluation? Well, the question pool offers three. One is calculation based on FCC OET bulletin number 65. Another offered is calculation based on computer modeling. And the other is to measure the field strength with calibrated equipment. All three of those answers appear in one question, which means that all of the above, I believe, is the answer for that one. So again, from the question pool in italics, what's an instrument that can accurately measure an RF field strength? Well, it's a calibrated field strength meter with a calibrated antenna. You can homebrew your own field strength antenna and you can get relative readings, but they don't really mean anything. You need to have a calibrated field strength meter and a calibrated antenna to accurately measure an RF field strength. So that's, option 3 in the list above you could do, but you would need a calibrated field strength meter and calibrated antenna. Okay, more about the RF exposure guidelines. So let's think about the criteria that we just seen. Oops, I'm sorry. I jumped ahead a slide in my mind. Let's talk about the factors determining RF exposure from the transmitted signal. Duty cycle is one of those. The frequency is another one, and the power density. So again, all three of those potential answers are offered up in one question. So in that question, all three of these choices are correct, would be the right answer. So duty cycle frequency, we taught that some of this goes back to the technician exam. The human body responds differently to different frequencies, which is why the frequency comes into play. For example, maximum permissible exposure value is actually lower on 50 megahertz, a 6-meter band, than it is on 3.5 megahertz, the 80-meter band. And that's because the human body effectively absorbs energy more efficiently at 50 megahertz than 3.5. So, and again, this relates to the notion of modulation duty cycle on RF exposure. What is the effect of modulation duty cycle on RF exposure? Well, the correct question correct answer to the question is lower duty cycles permit greater transmit power levels. So what's a lower duty cycle modulation? Something like single sideband is got a fairly low modulation duty cycle. There's a table in the study guide that lets you compare modulation duty cycle. A lot of digital modes, FM, are going to be a very high modulation duty cycle. But answer to the question, lower duty cycle permits greater transmit power levels. Okay, so let's talk about the FCC and their RF exposure guidelines. So in reality, your station is likely to fail to meet the RF exposure exemption criteria. What that means is your station probably isn't going to be in that less than a milliwatt of time averaged power. So and the question is, what happens if you fail to meet the RF exposure exemption criteria? Well, the answer is you need to perform an RF exposure evaluation in accordance with FCC OET bulletin number 65. So if you fail to meet it, which you're likely going to, you need to perform an RF exposure evaluation. So what happens if that evaluation shows that RF energy radiated exceeds the permissible limits? So you went through step 1, okay, I did the evaluation, shows that the energy exceeds the permissible limits, now what? Well, at that point, you must take action to prevent human exposure to excessive RF fields. So when the evaluation shows RF energy exceeds the permissible limits, you have to take action to prevent human exposure. This is kind of parallel to that. So what are precautions that you should take when installing an indoor transmitting antenna? Some folks can sneak an antenna up in their attic, especially if they're in um, a homeowner restricted area. So if you are going to install an indoor transmitting antenna, you must make sure that the MPE, that's maximum permissible exposure limits, are not exceeded in occupied areas. So precautions when installing an indoor transmitting antenna, make sure the MPE limits are not exceeded in the occupied areas. Okay, one more question in this train of thought here. And what happens if a neighbor might experience more than the allowable limit of RF exposure from, and this is key, the main lobe of a directional antenna? So you got a nice beam antenna sitting there at your station, and you can turn it any way you want. But if it's pointed to the main lobe of that antenna is at your neighbor's house, and there's a chance that it might exceed the RF exposure for your neighbor, what do you have to do? Well, you need to take precautions and ensure that that antenna is not pointed in your neighbor's direction. The answer says when present. I would say when present and transmitting. If your transmitter's on and your neighbor is home, don't have that directional antenna pointed in their direction. Okay, few more questions here, and we're going to be done with this section. What's the effect of modulation duty cycle on RF exposure? Um, Higher duty cycle transmitters exempt? No, are exempt? No, there's low duty, high duty cycle. You can eliminate C and D right off the bat. That takes you down to A and B. And the answer is the lower duty cycle permits greater power levels to be transmitted. And that makes sense. If the duty cycle, which is what percentage of the time the transmitter is actually sending out energy, if that's lower, then you can actually have higher power levels and still be within the RF exposure limits. Which of the following is used to determine RF exposure from a transmitted signal? Its duty cycle, its frequency, its power density. All of those come into play. So that's one of the answers where all of these choices are correct. All of these factors go into determining the RF exposure from a transmitted signal: duty cycle, frequency, and power density. What type of instrument can be used to accurately measure an RF field strength? Well, oscilloscope, nope. SWR meter, nope. Receiver with DSP, noise reduction, what? Boy, they made up some lousy choices there. The easy answer is a calibrated field strength meter, the calibrated antenna. And again, you'll find the answer in the question. The question ends in field strength. You look for the one answer that has field strength meter in it, and you've got the right one. What must you do if your station fails to meet the FCC RF exposure exemption criteria? Well, it's not as bad as it sounds. All you have to do is perform an RF exposure evaluation in accordance with FCC OET Bulletin 65. And remember, there's a couple of ways you can do that. You can use computer modeling. You can actually measure the strength. But if you fail to meet the exemption criteria, which is under a 1 milliwatt time averaged, yeah, so there you go. And oh, how about that? What does time averaging mean when evaluating an RF radiation exposure? Well, it's the total RF exposure averaged over a certain period of time. That's it. We're at the end of G0, electrical and RF safety. And yeah, there's only 2 questions on the exam. But as I said at the beginning, do not underestimate the importance of this, because there are certain aspects of this hobby that have dangers, potentially lethal dangers associated with them.
This is going to be section G2 out of the book, out of the exam pool. It's called Operating Procedures. I think everybody was here last week when I did G4, but again, I'm Peter, KN6UAW. Um, and we've got lots of questions to cover tonight, unfortunately. So there are 5 exam questions out of this section. There are 5 groups in this section, and there are 60 questions altogether. And it covers a fairly broad spectrum of topics, including good practices, making contacts, modes, HF, transmitting and receiving, emergency operations, volunteer monitoring, packet-based modes, some digital mode work, and some digital operating procedures. As is the case, if you have a question, please drop it into the chat, and hopefully I will notice it, and if I don't, we'll get it at the end. Let's get started. So let's talk about good practices. I do try to give you a reference into the general class license manual where these topics are covered. For this particular section, first and foremost, NATO phonetics are recommended and the most common. So Alpha, Bravo, Charlie, Delta, etc. If you're not using them now, I do encourage you to memorize them and start using them on VHF nets. It's a great place to practice. When you're on HF, and this is true on VHF and UHF as well, always listen first. You never know who's out there. You may only hear one side of a conversation, particularly on HF. And so it's just a good practice to tune to a frequency that you're thinking about transmitting on, listen for a bit, see if anybody else is out there. Follow Part 97, FCC Part 97, frequency and mode restrictions, as well as the band plan to stay within your general license privileges. And I do have a couple examples on the next couple slides. The band plans are conventions established by amateurs for how a particular band is going to be allocated and utilized. And so there are band plans. They sometimes are regional, sometimes national, sometimes within the context of a particular international telecommunications union region. If I recall correctly, we are in region 2. That's not on the test. Unlike VHF, clear HF frequencies are rare and unusual. Find a frequency where you will experience minimal interference and follow the recommended signal separation for continuous wave or CW. It's 150 to 500 hertz. For single sideband, it's 2 to 3 kilohertz. You want to tune to a clear frequency and listen. On a phone, ask, is this frequency in use? This is Kilo November 6 Uniform Alpha Whiskey. Again, is this frequency in use? Wait a few seconds, see if anybody replies. Sometimes I'll tend to wait, 5 to 10 seconds just as a general practice, but whatever you're comfortable with. No amateur has priority access to any HF frequency except in an emergency. So the key here is listen and be flexible. And then there's a question on split operation. So, and split operation is typically used by contesters. And what that means is that you are listening on one frequency and you're transmitting on a different frequency. And so the idea is that you can continue to transmit. Other people can hear you while you're transmitting. You'll only hear them if they dial to the frequency that you're listening on. And in a contest, folks are typically listening, anywhere but roughly 5 kilohertz up or 5 kilohertz down. So let's get to the amateur radio bands. This is in every ARRL licensing manual. I have a laminated copy tacked to the wall next to my radios. And I find it highly useful, and I would recommend anybody who's doing any HF work under your general license to have a copy of this, because you can see specifically where you're allowed to operate, where you're not, what your power levels are, what areas of the band are CW or data or phone, and it just helps you stay within conformance of the FCC rules. Here's an example of the 40-meter band plan. I think this is for the US, it might be for California. I think they're the same actually though. And it just gives you a sense of, particular areas on the band where you might find somebody. So at 7040 megahertz, you're going to find people doing DX data and DX ready. The ARRL runs a CW listening test on a regular schedule, and you can always find that at 7.0475 megahertz, for example. So there's a band plan for each of the bands. This is just one example. This is not on the test, although there is a question about an area of the band. Let's talk about the questions that are under the good practices section. So which of the following is true concerning access to frequencies? Well, we did cover that. Except in emergencies, no amateur station has priority to access to any frequency. What is good amateur practice if propagation changes during a contact, creating interference from other stations using the frequency? This is very true on HF, much less true on VHF. The bands change. They'll change, over the day. They'll change within a 5-minute period. You could be talking to someone and band conditions will change while you're in the middle of that conversation. So the key there, and I'm talking about a different question. My apologies. I got ahead of myself. So avoid creating interference by, if you experience interference, you're on a frequency, somebody else is on that frequency, and you both want to use it talking to different people, find a way to mutually resolve the situation in a nice, friendly way. Again, you don't have priority access to any band or any frequency, so the idea is share nicely. When selecting a CW transmitting frequency, what minimum separation from other stations should be used to minimize interference to stations on adjacent frequencies? CW is a narrow bandwidth transmission mode, so you only need between 150 hertz and 500 hertz between you and any other signals that are transmitting at that point in time. When selecting a single sideband transmitting frequency, what minimum separation should be used to minimize interference to stations on adjacent frequencies? With single sideband, you want to have a separation of 2 to 3 kilohertz. How can you avoid harmful interference on an apparently clear frequency before calling CQ on CW or phone? The important part of the answer here is find out if the frequency is in use. So send QRL on CW, and we'll talk about the Q codes in a bit, followed by your call sign. And if you're using phone, i.e. like SSB, ask if the frequency is in use, followed by your call sign. So you might say something in a phone model is this frequency in use? This is Kilo November 6 Uniform Alpha Whiskey. And then you wait a bit. Which of the following complies with commonly accepted amateur practice when choosing a frequency on which to initiate a call? Follow the voluntary band plan. You don't need to listen for 2 minutes. You should listen for some number of seconds, but you don't need to listen for 2 minutes. And you don't generally get in a situation where you're transmitting your call sign 3 times in a row. So again, follow the voluntary band plan. Which of the following are examples of the NATO phonetic alphabet? Well, the easy one here, if you only want to memorize one phonetic letter, memorize alpha, and that'll get you the right answer here. It's Alpha, Bravo, Charlie, Delta. There are no country names in the NATO phonetic alphabet, although there is a province name, Quebec. So alpha will get you the right answer, though. So let's talk about making contacts. And I'm kind of harping on this to some extent, but it's super important on HF. Listen first, and then check that the frequency is not in use. I would do CQ, CQ, CQ. This is Kilo November 6, Uniform Alpha Whiskey. Again, this is Kilo November 6, Uniform Alpha Whiskey, calling CQ. So some variation of that. You say that once or twice, and then you listen, see if anybody responds. If you don't hear anything in 5 or 10 or 15 seconds, try it again. And if you keep at it, you will usually get someone who's interested in talking with you. CQDX is seeking a contact outside of the continental 48 states. So you're looking for contacts, assuming you're in the continental US, you're looking for contacts in Alaska or Hawaii or any other country around the world. If you want to break into an existing conversation, also known as a QSO, you say your call sign once during a break in the conversation. And the folks in that conversation, if they want to acknowledge you, they will, and they'll invite you into the conversation. The 6-meter band plan, in particular, calls for DX between 50.1 and 50.125 megahertz. This is just something you need to memorize for the test. And the FCC may ask you for information about your transmitting activity. And so it's important to keep some kind of log of your activity. You can do it on a computer. There are many, many computer logging programs for both Windows and Macs. You can do it on paper. You can do it in an Excel file, et cetera, et cetera, et cetera. But it is considered generally good practice to maintain some kind of log when you're on the air. And then the other thing you want to do is you want to keep a record of your antenna gain. And so if you buy an antenna, that antenna will come with a specified gain. It might be 0 dB gain, it might be a 3 dB gain, it might be a minus 3 dB gain, depending on the type of antenna you're dealing with. But if you build your own, you can guess is probably the best idea. And if anyone else has a better answer for that, I'm happy to hear it. So questions under this section: what is the recommended way to break into a phone contact? We just talked about that. Say your call sign once during a break in the conversation. Generally, who should respond to a station in the contiguous 48 states calling CQDX? This would be any station outside the lower 48 states. What is a voluntary band plan restriction for U.S. stations transmitting within the 48 contiguous states in the 50.1 megahertz to 50.125 megahertz band segment? This is the one you want to memorize. So only contacts with stations not in the 48 contiguous states. Which of the following is good amateur practice for net management? We didn't talk about this explicitly, but in HF, the conditions may change, as I did mention. And so, most HF nets, if not all of them, have a plan in place that says if we lose our ability to communicate on this particular frequency, then we're going to try 5 kilohertz down, or we're going to try 5 kilohertz up. Or instead of being on 3.582, we're going to move to 3.977. Things like that. So essentially have some kind of a backup. Which of the following indicates that you're looking for an HF contact with any station? Repeat CQ a few times, followed by this is, then your call sign a few times, then pause to listen, and repeat as necessary until you make a contact. Why do many amateurs keep a station log? It's to help with a reply if the FCC requests information about your station. And the FCC has the right to ask information about any station at any point in time. They don't need a justification for it. They can just ask. Which of the following is required when participating in a contest on HF frequencies? Identify your station according to normal FCC regulations. Just because it's a contest and the contesters are trying to move quickly does not eliminate the need to follow FCC rules. And the primary FCC rule here is to identify your station. So let's talk about modes. The analog modes are CW, which is also historically known as Morse code. It usually occurs in the band areas reserved for CW, although anywhere in any band is allowed. So you can hear CW transmissions across the band sometimes. But mostly people that are doing CW are staying in the area that's specifically dedicated for CW. Single sideband is the most common phone signal in HF. And single sideband is an AM signal. If you recall from technician licensed environment, AM has a carrier and it has a sideband below the carrier and a sideband above the carrier. And what happens with single sideband is you actually suppress the carrier and you suppress one of the sidebands. The benefit of doing that carriers and single sideband suppression is that you end up with a much lower bandwidth signal, in this case, 3 kilohertz wide signal. Good amateur practice is to use upper sideband on 20 meters and above and lower sideband on 40 meters and below. That's a practice, not a rule. So you can do it differently, but people aren't going to hear you unless you've set up some convention with somebody that you want to do USB on 40 megahertz or in the 40 meter band. The 60 meter band is special and it specifically requires that you use upper sideband on the 5 channels that are available there. Other modes include digital voice, digital data modes, and image modes. A variety of ways to send information over a radio within the bands that are available to amateur licensees. Which mode is most commonly used for voice communications on frequencies of 14 megahertz or higher? 14 megahertz is a 20 meter band, and so that's upper sideband. Which mode is most commonly used for voice communications on the 160, 75, and 40 meter bands? This is lower sideband. 40 meters and below is lower, 20 meters and above is higher. Which mode is most commonly used for SSB voice communications in the VHF and UHF bands? Again, we're above 20 meters, so it's going to be upper sideband. And you do hear SSB conversations going on VHF and UHF sometimes. Which mode is most commonly used for voice communications on the 17 and 12 meter bands? A lot of repetition in these questions. It's again upper sideband. And which mode of voice communications is most commonly used on the HF amateur bands? And this is single sideband. You can use FM, you can use AM, but SSB is the most common. Which of the following is an advantage of using single sideband as compared to other analog voice modes on HF amateur bands? It's all about bandwidth. So it's less bandwidth used and greater power efficiency. Which of the following statements is true of single sideband? Only one sideband is transmitted. The other sideband and the carrier are suppressed. And they're suppressed by the transmitter before the signal leaves the antenna port on the back. Why do most amateur stations use lower sideband on the 160, 75, and 40 meter bands? Because it's a commonly accepted amateur practice. All right, let's talk about HF receiving. A wide area of content here, frankly. So there's a little bit in the exam that we'll cover. There's a lot of other things of interest in HF receiving, but this is what the exam is going to cover. So QRN, the Q signals are 3-character signals. They came out of the telegraph era and they've been carried forward into the ham era, and they're super helpful if you are using ones that you're familiar with, and it's really bad when you hear ones like, oh, I have no idea what that one means. So you pull out the chart and look it up. For the exam, QRN is on the exam, and the N is for noise or static. That's the best way to remember it. And the HF bands generally have some kind of noise or static going on. Sometimes it's below the S meter. You can't see it on an S meter. Sometimes you're on a particular band and the noise level is at an S5 or an S6 or S7 or S8. And you can't hear anybody unless they're like next door and you're getting ground wave signal into your antenna. It's also great being on a band watching the lightning storms and the thunderstorms go by, and not necessarily in your area, but somewhere else in the world, because all of a sudden you're pantograph lights up with, lots of noise for a second or two, and then it kind of fades away. That's a storm or some other thing going on in the atmosphere. And the noise exists on all bands. It varies by time of day, by time of year, by sunspot activity, which I know we've covered in previous sessions. So just to be aware. Most HF contacts exchange a signal report so that adjustments can be made if necessary to accommodate the conditions. And those signal reports are called RST reports, or readability, strength, and tone. If you're using phone, it's really just readability and strength. Readability goes on a scale of 1 to 5, with 5 being the best. Strength goes on a scale of 1 to 9, 9 being the best. So if somebody is booming into your station at an S9 plus 20 signal, you would typically label that as a 5.9 signal report. If you're hearing somebody just above the noise and you can actually make out what they're saying, that might be like a 3.3 or a 4.4 kind of signal report. So, if they're down in the noise and you can't really hear them, you could be in a 1 or a 2 situation, but they're not going to hear you probably either, and they'll never get your signal report. The tone element, or third element of an RST report, is used when you're doing CW and digital. Tone also is a 1 to 9 scale, 9 being the best. So a 5.99 in a CW signal situation means that you're hearing them super clear. A C is added to the tone report on CW when the signal is chirpy or unstable. So you may have a 5.4.4C if you're getting kind of a mediocre, or a 4.4.4C for mediocre CW signal. So questions in the receiving section. When sending CW, what does a C mean when added to the RST report? Chirpy or unstable signal. What does the Q signal QRN mean? I am troubled by static. N for noise or N for static is the best way to think about it for me. Why are signal reports typically exchanged at the beginning of an HF contact? This is to allow each station to operate according to conditions. So then let's talk about transmitting. Like I said, the receiving stuff skims the surface in this section of the questions. We're going to talk mostly about CW procedures, and then we'll talk about some Q signs. CW transmission, so your transceiver can generally be configured when sending CW to be either semi-break-in or full break-in. And what semi-break-in means, back up, Peter. The other thing that your transmitter can be configured to do is to use push-to-talk, a little button on the hand and the hand mic, or a foot button if you're using a table mic, or Vox, which is voice activated. And so if you're doing CW, you're typically in Vox operation because you're using a key, and you want, when there's a tone from the key, you want that tone to be transmitted by the transceiver. So you don't want to be doing any PTT stuff. So semi break-in is where the transceiver switches back to receive once the Vox timeout period has expired, and that's usually on the order of some milliseconds. Or full break-in is where the radio switches between transmit and receive within a few microseconds. So when you're operating full break-in, it gives you the ability to hear other people transmitting CW at the same time that you're transmitting. So you could transmit a particular character, stop transmitting, to, you're pausing for the next character, and your receiver picks up as somebody is transmitting on that same frequency. That's what full break-in means. Semi break-in means you'll probably miss most of it. Full break-in means you'll probably get most of it. In the context of CW, there are these things, these 2-letter abbreviations called pro signs. Again, these came out of the telegraph era. AR, the pro sign AR indicates end of message. And the pro sign KN tells others that you're only interested in hearing from a specific station. And the pro signs are used to reduce the number of characters that have to be transmitted when you're sending CW. That's the basic idea there. When you are doing CW with someone and you respond to a CQ, you respond at the fastest speed that you're capable of sending, but you want to respond no faster than the speed of the sending station. So you want to be sensitive to what speed they're sending at so that you don't exceed their speed, because they may not be capable of hearing, of transcribing your transmission any faster than what they're sending at. And then the other thing you want to do is you want to exactly match your transmitting frequency to the received signal so that you achieve what's called zero beat. So there's basically no difference in transmit and receive frequency, and your CW tones sound crisp and clear, and theirs sound crisp and clear. And I mentioned Q signals. These are additional abbreviations. They're used both on CW and phone. The Q signal QRS tells the sender to send slower, S for slower. QRV indicates that you're ready to receive. QSL tells the sender you've received and understood their message. QSL is used a lot in phone transmissions, particularly if you've heard of something called Parks on the Air. The groups that do POTA transmissions generally use QSL quite a bit just to make sure that they're being heard and that you're hearing them correctly. And then QRL is Q code for Q signal for is this frequency in use? Is this frequency busy? These are things that, you know, once you get on HF, you'll start using some of them. For the test, you just need to memorize them. It's just because they're going to, one of them for sure is going to show up on the test. And then in all cases with transmitting on any frequency, in any mode, in any band, you do need to give your call sign every 10 minutes and at the end of any transmission. So transmitting questions. What does the Q signal QRL mean? Are you busy, or is this frequency in use? Which of the following statements is true of voice-operated operation versus PTT operation? It allows hands-free operation, so you don't need a finger or a foot pushing the push-to-talk button. Which of the following describes full break-in CW operation, also called QSK? Transmitting stations can receive between code characters and elements. What should you do if a CW station sends QRS? You should send slower, so S for slower. What does it mean when a CW operator sends KN at the end of a transmission? Listening only for a specific station or stations? What is the best speed to use when answering a CQ in Morse code? Again, the fastest speed at which you're comfortable copying, but no faster than the sender. What does the term zero beat mean in CW operation? It means you're matching the transmit frequency to the frequency of the received signal. And what pro sign is sent to indicate the end of a formal message when using CW? It's the AR pro sign. And what does the Q signal QSL mean? I have received and understood. What does the Q signal QRV mean? I am ready to receive. And what is QRP operation? So QRP, we didn't talk about, but it is low power. So typically if you're using a handheld radio, 5-watt radio or less, or if you're using a base station, but you've got the transmit power dialed down to say 5 watts or sometimes even 10 watts, that's considered low power operation. And there are groups that specialize in low power transmitting and receiving. There are contests that are QRP contests. Lots of stuff going on with very low power situations. All right, let's talk about emergency operations. There are actually two separate and somewhat overlapping organizations that deal with emergency operations and that are involve ham radio operators. So the RACES organization, also which is the acronym for the Radio Amateur Civil Emergency Service, RACES is sponsored by government agencies. It is specifically intended for civil defense, and an FCC licensed amateur who has received a certification from a civil defense organization can be a RACES member and participate in RACES activities. And then one little odd question on the test is RACES drills may not exceed 1 hour per week. ARES is another organization. This is the Amateur Radio Emergency Service. It's sponsored and organized by the ARRL. And ARES provides communications assistance to local and regional governments and relief agencies. In terms of distress calls, if you hear a distress call on a frequency that you're on, you should suspend any existing contact conversation, and you should acknowledge to the station calling for help that you hear them. And then you want to stand by to receive the location of the emergency and the nature of the assistance requested. So you need to ask them, where are you and what is going on and what kind of assistance are you asking for or seeking. You should relay that information to the proper authorities. Usually you do that by phone. If you have a telephone or if you have internet, you can get on the internet and do it that way. But there could also be emergencies when there isn't. Part of what we do is emergency communication when the internet's down and the cell networks are down. And in that case, if you get an emergency like this, then you can generally switch to a net that would be operating in that emergency and relay information through that net with the idea of getting it to someone on the net who actually still has cell phone coverage or telephone coverage of some kind or internet coverage of some kind. But then you got to go back to the person who's calling you with the emergency and stay there until you can get further information from them if there's more information coming or until help arrives. The key with an emergency situation, if you're experiencing an emergency, is that you can request emergency help using any means of radio communication available. So any frequency, any mode, any power level, regardless of any license restrictions that you might have. So if you, for example, have a technician license and there's an HF radio nearby and you can get on to 20 meters and call for help on 20 meters, you just go ahead and do it. That is perfectly appropriate in an emergency situation. So questions under this topic. How often may RACES training drills and tests be routinely conducted without special authorization? No more than 1 hour per week. What is the first thing you should do if you are communicating with another amateur station and hear a station in distress break in? Acknowledge the station in distress and determine what assistance may be needed. Who may be the control operator of an amateur station transmitting in RACES to assist relief operations during a disaster? Only a person holding an FCC-issued amateur operator license. This is a little bit of a tricky question because the answer is kind of incomplete because you can only transmit in RACES if you have a certification from a sponsoring organization. But you can't transmit in RACES at all if you don't have an FCC issued license. So that's why the answer is only a person holding an FCC issued amateur operator license. None of the other answers apply. All right, volunteer monitoring program. The amateur service is largely self-policing. There are no FCC amateur radio licensing police. The VM program's goal is to encourage self-regulation and rules compliance. Volunteers are formally enlisted to monitor the airwaves for rules violations. And you actually, if you are an ARRL member, there's usually a little section in one page in every month's QST magazine where they talk about significant monitoring notifications. So I think in the last couple of months, the number of hours that were monitored were like 3,500 hours on a particular frequency. And there were 2 compliance issues that one was dealt with and one was reported up to the FCC. So it's people that are specifically on frequencies listening for people who are behaving improperly. And then there's a question about triangulating the location of a violating station. So I think we've talked about fox hunting in other situations, but essentially 2 or 3 people get together and you triangulate using beam antennas to find out the location of a third-party transmitter. So questions: what is a volunteer monitor program? Amateur volunteers who are formally enlisted to monitor the airwaves for rules violations. Which of the following are objectives of the volunteer monitor program? To encourage operators to self-regulate and comply with the rules. What procedures may be used by volunteer monitors to localize a station whose continuous carrier is holding a repeater on in their area? Do a little fox hunt, compare beam headings on the repeater input from their home locations with that of other volunteer monitors. All right, now we're going to do a fairly deep dive into packet-based modes. And this is 5 pages in the book, which is fairly short because there's a lot of detail here. But let's get going. So packet-based really just means structured data. For those of you who have worked with computers, you know, computer networking is a packet-based or structured communication mode. So computers talk over the internet with other computers, and there are protocols established that enable those communications to occur. If for radio, the packet-based modes used in radio were derived from the computer-to-computer networking modes, as well as from teletype over radio communication modes in the past. Packet-based modes require computer control of your transmitter and your receiver. So you can't do packet listening like you can with CW or phone. There are several modes, 2 in particular, JT65 and FT8, that require very precise timing. So your computer clock has to be synchronized to within 1 second of standard time. At this point in the technology, I think that's pretty common. I know my Mac syncs with a network time server. I believe Windows systems now sync with the network time system. So you want to make sure that you're on the internet when you're doing this because you want your clock synchronized like that. Packets are just structured groups of information. They typically have a header, they have a chunk of data, and they have a trailer. The header provides synchronization between the transmitter and the receiver. Usually it has a sequence number in it. It may have other information in it. It could have who the sender is. I could have who the desired receiver is, etc. Lots of stuff could get shoved in the header. Primary purpose is synchronization. The trailer provides additional control care information, status information. It may also provide error detection or error correction information. So when you send a data signal over the radio, you know, some of that data may get through, some of it may not. Hopefully it all gets through, and hopefully the signal isn't too degraded so that the receiver can receive it all and decode it all. But if it can't, or if the data chunk gets corrupted in some way, you can send error detection and correction information, which is essentially just redundant information that's sent along in the packet. ARQ is a mode where the receiver sends a NAC, which is a not acknowledged abbreviation. So a NAC message is sent by the receiver when a mismatch is detected between what the receiver received and what the error detection or redundant information, if you will, indicated should have been received. Two packet-based modes, one called Pactor and the other called Packet Radio, both use ARQ. Other digital modes also use ARQ. A key point with ARQ-based communications is that they are point-to-point between one transmitter and a single receiver, and they cannot be broken into like CW or a phone. WinLink is another packet-based mode, and it enables transferring email and digital files using digital modes on HF bands. WinLink is an existing worldwide communication system, and it can facilitate email exchanges between amateur radio operators without internet access. So you can basically, on your computer, create an email, initiate your WinLink application, which sends out email through your radio to the WinLink radio network. And if somebody's in receive range with a WinLink gateway running, that message will be picked up and will be available for the recipient to pick up from one of the WinLink environment servers. WinLink can also be connected to the internet, and it can also basically forward messages from a radio to the internet. So that's another way to get information sent around. And then specifically, WinLink uses several modes on HF. Pactor and VARA are both common modes. Other packet-based modes, we mentioned FT8 briefly a minute ago, and then Whisper, WSPR. There's a digital software package called WSTJ-X, or software suite. And this is a set of applications that have been developed by ham radio operators to do digital communications. FT8 and Whisper both use precisely timed sequences. They use 8-tone frequency shift keying modulation and sophisticated error decoding and correction techniques. They both operate successfully in very low signal to noise environments. So high noise environments you can still do FT8 in. One of the limitations of FT8 is that the information that can be exchanged is pretty limited. It's call signs, grid locators, and signal reports. For FT8 in particular, the signal report is specifically the signal to noise level. So a report of +3 means 3 dB above the noise floor for your signal. There's a lot of FT8 on HF radio. Lots of people are using it. It's a great way if you want to just make a lot of contacts. AREDN is the Amateur Radio Emergency Data Network. This takes a commercially available internet router and swaps out the firmware and the software. It runs different software, and you can set up a peer-to-peer self-discovering network that can be used by radio operators. It's typically used during emergencies, for example, when the internet goes down, and it's sometimes used for supporting large community events as well. Okay, let's talk about a number of questions under this topic. So what is VERA? VERA is a digital protocol used with WinLink. So VERA is essentially the description of how the WinLink information is sent from one radio to another radio. Which of the following is good practice when choosing a transmitting frequency to answer a station calling CQ on FT8? The FT8, you want to find a clear frequency during the alternate time slot to the calling station. And this is a level of minutia associated with FT8 that I suggest, if you haven't done FT8, just memorize the answer for the exam. Once you get into FT8, this will become very apparent why you do this. But for the exam, just know you need to find an alternate time slot on a clear frequency. Which of the following is required when using FT8? Computer time accurate to within approximately 1 second. How do you join a contact between two stations using the backdoor protocol? You don't. Joining an existing contact is not possible. Backdoor connections are limited to 2 stations. What is the primary purpose of an amateur radio emergency data network, mesh network? It's to provide high-speed data services during an emergency or community event. Which of the following describes WinLink? An amateur radio wireless network to send and receive email, a form of packet radio, and a wireless network capable of both VHF and HF band operation. So the answer is all of the above. What is another name for the WinLink remote message server? I briefly touched on this. It's called a gateway. And this is the piece of equipment that will get the message from you when you send it. Which of the following is a common location for FT8? Oh, I didn't talk about that. I apologize. 14074 to 14077. On the band plan at the beginning of the presentation, this is actually mentioned. It is shown. It shows up in that section of the band. Again, something you just need to memorize for the exam. All right, receiving and transmitting digital modes. Most digital modes on HF are transmitting as upper sideband signals, except RIDI, which has traditionally used lower sideband. Your modem must be configured for the correct baud rate and tone frequencies. And we've talked about baud rate at different sections of this class. If you're using the wrong SSB mode, let's say you're using LSB instead of upper sideband, that inverts the tone relationship, and then the receiver can't decode the data. If you're using the wrong baud rate, then the receiver's not going to be able to decode the data. If you're using the wrong tone frequencies, the receiver's not going to be able to decode the data. So which mode is normally used when sending RIDI signals via audio frequency shift keying with an SSB transmitter? Lower sideband. What is the standard sideband for JT65, JT9, FT4, FT8 digital signal when using audio frequency shift keying? The convention is upper sideband. What could be wrong if you cannot decode a RIDI or other frequency shift key signal, even though it is apparently tuned in properly? All of these are correct. So the free mark and space frequencies might be reversed. You might have selected the wrong baud rate, or you might be on the wrong sideband. Digital operating procedures, and we are closing in on the end of this long conversation here. So thanks for hanging in there. So digital. Unmanned gateways and mailbox stations monitor a fixed frequency waiting for another station to connect. So for example, a WinLink gateway will monitor a particular frequency, sometimes at a particular point in time, listening for transmitters like me or you who want to send a message. The connection establishment is protocol specific. So whether you're using Pactor or Vera or some other protocol, but the contact always starts with a connect message. So my WinLink system sends a connect message to an unmanned gateway or a mailbox station asking to connect. Again, these are point-to-point communications and they cannot be broken into by another station. Doesn't mean they can't be interfered with, but they can't be broken into. So you can't have a three-way digital conversation. You have a two-way point-to-point digital conversation, unlike a phone conversation where you can have 3 or 4 or 10 people in. ARQ modes such as Pactor and Vera will do their best to automatically recover from reception difficulties, but interference can cause a failure to connect. It can cause frequent retries or transmission delays, or it can cause timeouts or drop connections. What symptoms may result from other signals interfering with a Pactor or Vera transmission? All of these are correct. Frequent retries, long pauses in message transmission, or failure to establish a connection between stations. Which of the following is a way to establish contact with a digital messaging system gateway station? Transmit a connect message on the station's published frequency. All right, and then we have what I label my classic miscellaneous questions that don't fit anywhere else. So I've got another band plan example following this. The ready frequency shift, so the mark and tone frequencies are typically separated by 170 hertz. And that's just a convention that's been in place for many, many decades. Automatic level control, which we talked about last week, is typically adjusted by changing the microphone gain or the transmit audio control. I believe Tim talked about azimuthal projections, but this is a map that shows true bearings and distances from a specific location, typically your location, to other locations around the world. And it's very helpful if you want to establish a short path or you want to see what your short path is currently to a particular part of the world. And then the long path is basically looking behind the short path. So the long path is 180 degrees from the station's short path. So instead of me short pathing to, let's say, Montreal, the long path would go backwards around the globe to Montreal the long way. Here's an example of a digital signal band plan. These are the areas on the different bands within the IRU region 2, our region. A lot of these line up with band plans in other regions. That's how come we're able to talk to people around the world. And the example here that shows up on a test is the 20 meter 14.070 to essentially 14.1 megahertz as part of the digital band. So the questions: in what segment of the 20 meter band are most digital mode operations commonly found? I just answered that for you. 14.070 to 14.100. What is the most common frequency shift for RTTY transmission, RTTY emissions in the amateur HF bands? It's 170 hertz. What control is typically adjusted for proper ALC setting on a single sideband transceiver? It would be the transmit audio or microphone gain. Which of the following describes an azimuthal projection map? This is the map that shows true bearings and distances from a specific location. How is a directional antenna pointed when making a long path contact with another station? It's pointed 180 degrees from the station's short path heading. And that is that.